Right now, as you listen to these words, you are suspended on a small blue planet, drifting through an ocean of darkness that extends beyond all human comprehension. The general rotation of Earth is carrying you through space at over 1,000 miles per hour, yet you feel nothing of this cosmic movement. Your body is still, perhaps resting in the quiet comfort of your room, while your mind prepares to journey much further than your physical form ever could. Tonight, we will explore one of humanity's most profound questions. What would happen if we attempted to reach another galaxy? Not just visit a distant star within our own Milky Way, but truly cross the vast cosmic ocean to another island universe. The answers are both beautiful and unsettling. They reveal fundamental truths about our place in the cosmos and the nature of reality itself. They speak to our limitations as biological beings. It also showcases the remarkable power of human imagination. Our journey will take us through the physics of interstellar travel, the mind-bending distances between galaxies, and the cosmic timescales that dwarf our brief human existence. We will confront the harsh realities of such a voyage. But first, a promise. Though some of these truths may initially seem disheartening, there is profound wonder and even comfort to be found in understanding our cosmic context. The universe reveals itself to be far stranger and more magnificent than our ancestors ever imagined. As we travel together through these ideas, imagine yourself not confined to Earth, but as a cosmic explorer, untethered from the limitations of your physical form. Your consciousness can roam where your body cannot. The nearest major galaxy to our own is Andromeda, a vast spiral of stars that appears in our night sky as a faint smudge of light. Even this closest galactic neighbor is so distant that its light takes 2.5 million years to reach us. To grasp what this means, if you could travel at the speed of light, the cosmic speed limit according to Einstein's theories, it would take you 2.5 million years to arrive. The entire span of human civilization would pass many times over during your journey. And Andromeda is merely our next-door neighbor in cosmic terms. The observable universe contains roughly 2 trillion galaxies, scattered across distances so vast that our minds struggle to comprehend them. These numbers are not meant to overwhelm you, but to gently expand your perspective. There is something deeply calming about contemplating the immensity of the cosmos while safely nestled in our planetary home. Throughout human history, we have gazed at the night sky and wondered about these distant lights. Ancient civilizations created myths to explain them. Modern science has revealed their true nature, yet in some ways has only deepened the mystery. When we look at galaxies through our most powerful telescopes, we are actually looking backward in time. The light from Andromeda that reaches your eyes tonight began its journey when early humans were just beginning to use stone tools. This temporal aspect of our cosmic observations adds another layer of complexity to our journey. If we could somehow reach another galaxy, we would be traveling through both space and time in ways that challenge our everyday understanding of reality. Our documentary will explore the harsh realities of such a journey, the energy requirements that exceed our planet's total resources, the time dilation effects that would make Earth's civilization unrecognizable upon return, and the physical limitations of biological bodies. But we will also explore theoretical possibilities, generation ships where multiple human lifetimes pass during the journey, suspended animation technologies, and speculative physics that might, just might, offer shortcuts through the fabric of space-time. We will examine the psychological impact of such vast journeys. What would it mean for human consciousness to be truly isolated in the void between galaxies? How would we maintain our sense of purpose and connection across such timescales? The questions we'll explore touch on physics, biology, psychology, philosophy, and even spirituality. They reveal the interconnectedness of all knowledge when we confront the greatest distances imaginable. As you listen, allow these cosmic scales to wash over you. There is no need to grasp every detail at once. Like the light from distant galaxies, understanding will accumulate gradually, photon by photon, idea by idea. In the coming hours, we'll decode the mathematics of intergalactic travel, examine the energy requirements for various propulsion systems, and confront the biological challenges of sustaining human life for millennia in the void between galactic shores. We'll also explore what motivates this deep human desire to reach beyond our cosmic neighborhood. What are we really seeking when we dream of touching another galaxy? Perhaps understanding these motivations tells us something essential about our species. Chapter 2: Premise and Human Meaning. Why does this question, the possibility of reaching another galaxy, matter to us as we go about our daily lives on Earth? The answer lies in our fundamental nature as explorers and meaning makers, creatures who find purpose in stretching beyond known boundaries. Since our earliest days as a species, humans have been compelled to venture beyond horizons. We migrated out of Africa, sailed across vast oceans, climbed the highest mountains, and eventually left Earth's atmosphere to touch the lunar surface. Each expansion of our physical reach has transformed our understanding of ourselves. When we first saw Earth from space, a fragile blue marble suspended in darkness, it forever changed our perception of our planetary home. Contemplating intergalactic travel takes this perspective shift to its ultimate conclusion. It forces us to confront the true scale of cosmic time and space, dimensions so vast that they initially seem to render human existence insignificant. But this apparent insignificance contains a hidden gift. There is a peculiar comfort in recognizing our smallness against the cosmic backdrop. Our personal troubles, even our greatest global challenges, exist within a context of breathtaking grandeur. When you worry about tomorrow's responsibilities or replay yesterday's conversations, remember that you do so while riding a planet orbiting an average star in one spiral arm of one galaxy among trillions. This cosmic perspective doesn't erase your concerns, but it does reframe them. The immense distances between galaxies aren't just physical measurements. They're existential boundaries that help define what it means to be human. We are creatures adapted to live and think on a particular scale, in a particular corner of the universe. Our brains evolved to track seasonal changes, remember the locations of food sources, and navigate social relationships within small groups. They did not evolve to intuitively grasp light years or millions of millennia. Yet remarkably, we can still conceptualize these scales. This ability to transcend our evolutionary programming through mathematics, technology, and imagination is perhaps our species' most distinctive trait. We can think beyond our immediate surroundings in ways no other Earth species can. When we contemplate reaching another galaxy, we're stretching this uniquely human capacity to its limit. We're using our Earth-evolved minds to grasp distances so vast that they make the journey from Earth to Mars seem like a casual stroll by comparison. There's something profoundly moving about this cognitive reach. Even if we never physically traverse these cosmic distances, the mere fact that we can comprehend them and calculate what such journeys would require speaks to something remarkable about consciousness itself. Astronomers measure the distance to Andromeda in light years, but they might as well measure it in human lifetimes. At our current technological capabilities, it would take hundreds of thousands of generations to reach our nearest galactic neighbor. This sobering reality doesn't diminish the value of the question. Rather, it highlights a fascinating tension in our existence. We are simultaneously cosmic beings, made of elements forged in stellar explosions, and deeply local creatures tied to a specific world. Our bodies contain carbon atoms that once existed inside ancient stars. When those stars died in supernova explosions, they scattered these elements across space. Eventually, some of these atoms became incorporated into the molecular cloud that formed our solar system. In a very real sense, we are the universe experiencing itself. The same cosmic processes that created galaxies also, through an incomprehensibly long chain of events, created the consciousness that now contemplates those galaxies. This recursive loop, where the universe has evolved creatures capable of understanding the universe, gives a profound significance to our seemingly tiny existence. We may be small, but we are meaningful precisely because we can comprehend the vast. When you gaze at the night sky and spot the faint smudge of Andromeda, visible to the naked eye under dark skies, you're participating in something remarkable. Photons that traveled 2.5 million years are being processed by a brain evolved on a different world. The question of reaching other galaxies also forces us to consider time in ways that transcend our brief individual lives. It invites us to see ourselves as part of humanity's ongoing story, a narrative that extends both backward and forward in time. If humanity were to launch an intergalactic mission tomorrow, none of us would live to see its arrival. Neither would our children or our children's children for hundreds of thousands of generations. It would be the ultimate act of faith in our collective future. This temporal perspective offers another kind of comfort. Individual lives are brief, but we are part of something larger, a species-wide journey of discovery that began when the first humans looked up at the night sky and wondered what those lights might be. The harsh reality of intergalactic distances doesn't crush this human spirit of exploration. It contextualizes it. It reminds us that exploration happens in stages, across generations, with each discovery building on those that came before. Our ancestors couldn't have imagined spacecraft or telescopes, yet their curiosity about the heavens set humanity on a path that eventually led to these technologies. Similarly, we may not be able to imagine the technologies that will eventually bridge interstellar, and perhaps someday, intergalactic distances. There is deep meaning in this continuity of human inquiry, this passing of the torch of knowledge from one generation to the next. The question of reaching other galaxies connects us to both our past and our future in a single cosmic narrative. And perhaps most importantly, confronting the vast scales of the universe doesn't have to lead to nihilism or despair. Instead, it can awaken us to the preciousness of our brief moment of consciousness, our rare opportunity to witness the cosmos. Chapter 3: Origins and Early Science. The human fascination with the night sky predates recorded history. Our earliest ancestors looked upward with wonder, their lives governed by the rhythms of sun and moon, their navigations guided by the fixed patterns of stars that seemed eternal and unchanging. But it was the Greeks who first began to systematically ponder what those lights might be. Democritus, in the 5th century BCE, proposed that the Milky Way, that ghostly band of light across the night sky, might consist of distant stars too numerous to distinguish individually. This insight was remarkable, yet incomplete. No one in the ancient world could have comprehended the true nature of what we now know as galaxies, vast collections of stars, gas, and dust, each a universe unto itself. For most of human history, our understanding remained limited by what the naked eye could see. The Milky Way appeared as a cloudy path across the night, inspiring myths worldwide. In Greek mythology, it was spilled milk from the goddess Hera. The scientific revolution that began in the 16th century would eventually transform our cosmic understanding. But the breakthrough for galaxy science came with the invention and improvement of the telescope. Galileo first turned his modest instrument skyward in 1609. When Galileo pointed his telescope at the Milky Way, he confirmed Democritus' ancient speculation. The cloudy band resolved into countless individual stars, too distant to be seen clearly by the unaided eye. The universe suddenly expanded in human understanding. Yet even Galileo had no concept of other galaxies. The prevailing view held that the universe consisted solely of our Milky Way galaxy, with everything visible existing within its boundaries. The true scale of the cosmos remained veiled. As telescopes improved through the 18th and 19th centuries, astronomers began cataloging fuzzy patches of light they called nebulae. Some, like the great astronomer Charles Messier, compiled these objects primarily to avoid confusing them with comets, his main interest. Messier's catalog, first published in 1774, included what we now know as the Andromeda Galaxy, M31. But at the time, no one knew whether this spiral-shaped nebula was a distant collection of stars or merely a cloud of gas within our own galaxy. The debate intensified in the early 20th century. Some astronomers believed these spiral nebulae were forming solar systems within the Milky Way. Others suspected they might be island universes, entirely separate galaxies like our own at vast distances. This became known as the Great Debate. On April 26, 1920, astronomers Harlow Shapley and Heber Curtis formally argued their opposing views at the National Academy of Sciences. Shapley maintained the universe consisted only of the Milky Way. Curtis championed the island universe theory. The resolution came from an unexpected source: Edwin Hubble, working with the world's largest telescope at Mount Wilson Observatory. In 1923, Hubble identified a type of variable star called a Cephid in Andromeda. Cephids are crucial to astronomy because their intrinsic brightness is directly related to how quickly they pulse. By timing these pulsations, Hubble could determine the star's true brightness and from that, calculate its distance using a simple principle: apparent brightness diminishes with distance. When Hubble performed these calculations, the results were staggering. Andromeda lay far beyond the boundaries of the Milky Way, so far that it had to be an entirely separate galaxy. With this discovery, the universe suddenly expanded beyond all previous conception. Hubble announced his findings in 1924, settling the Great Debate and forever changing our cosmic perspective. Our universe wasn't just the Milky Way. It contained countless other galaxies, each with billions or trillions of stars, separated by almost unimaginable distances. This revelation represented one of the greatest perspective shifts in human history, comparable to Copernicus showing that Earth orbits the Sun rather than vice versa. Once again, humanity was displaced from the center of things. Our cosmic habitat revealed to be vaster than imagined. The 1920s brought another revolutionary discovery. By studying the light from these distant galaxies, Hubble and others realized that most galaxies show a redshift. Their light stretched toward the red end of the spectrum, indicating they're moving away from us. Moreover, Hubble discovered a pattern. The farther away a galaxy appears, the faster it seems to be receding. This relationship, now known as Hubble's law, provided the first observational evidence for an expanding universe, the foundation of modern cosmology. An expanding universe implied a beginning, a moment when all matter was compressed into an incredibly dense state before expanding outward. This concept eventually developed into what we now call the Big Bang Theory, the idea that the universe has been expanding for about 13.8 billion years. As our understanding of physics evolved through the 20th century, scientists began to grasp the profound challenges involved in traversing these cosmic distances. Einstein's theories of relativity, published in 1905 and 1915, established the speed of light as a cosmic speed limit. Nothing with mass, according to these theories, can travel faster than light, approximately 186,282 miles per second. This speed seems incredibly fast by human standards, yet painfully slow when measured against intergalactic distances. Light from Andromeda takes 2.5 million years to reach us. The light from more distant galaxies takes tens or hundreds of millions of years. The most distant observable galaxies are seen as they were billions of years ago, when the universe was young. Throughout the mid-20th century, science fiction writers imagined ways to overcome these limitations. The concept of hyperspace, warp drive, and other faster-than-light travel mechanisms entered popular culture, offering fictional solutions to very real physical constraints. Meanwhile, physicists explored the implications of relativity for any actual interstellar or intergalactic journey. They discovered that time dilation, the slowing of time for moving objects as they approach light speed, would create a profound disconnect between travelers and those left behind. This phenomenon, verified experimentally with subatomic particles and precise atomic clocks, means that a crew traveling at near light speed would experience time passing more slowly than those on Earth. The closer to light speed, the more pronounced this effect becomes. For a ship traveling at 99.9% the speed of light, a journey to Andromeda might take just over 2.5 million years from Earth's perspective, but the crew might experience only a few decades due to time dilation, a mind-bending consequence of Einstein's theories. As our understanding of both galaxies and physics matured, the practical challenges of intergalactic travel came into sharper focus. The energy requirements for accelerating even a small spacecraft to a significant fraction of light speed proved staggering. By the late 20th century, astronomers had discovered that galaxies are not evenly distributed throughout space, but form clusters and superclusters with vast voids between them. Our Milky Way belongs to the local group, dominated by our galaxy and Andromeda. This clustering means that some galaxies are actually moving toward rather than away from us. Andromeda and the Milky Way are on a collision course, expected to merge in about 4.5 billion years, a cosmic encounter that will transform both galaxies. Chapter 4. First Evidence and Scale. To truly comprehend the challenge of reaching another galaxy, we must first establish a sense of scale, starting with our own cosmic neighborhood and expanding outward. Our journey begins with the Earth, our planetary home, approximately 7,917 miles in diameter. Light, the fastest entity in the universe, circles Earth in just 0.13 seconds. At human scales, this seems instantaneous. A commercial airplane would take roughly 40 hours to circumnavigate our planet. These are distances we can grasp intuitively. Expanding outward, we reach the Moon, our closest celestial neighbor, approximately 238,855 miles away. Light crosses this gap in just 1.3 seconds. The Apollo astronauts made the journey in about 3 days, the farthest humans have ever ventured from Earth. The Sun, the center of our solar system, sits 93 million miles away. Light from its surface takes 8.3 minutes to reach us. If the Earth were the size of a marble, the Sun would be a ball about 9 feet in diameter, and the distance between them would be about 1,000 feet. Voyager 1, our most distant human-made object, launched in 1977, has been traveling for over 45 years and has only recently entered interstellar space. It moves at about 38,000 miles per hour, yet would take 73,000 years to reach the nearest star system. Proxima Centauri, that nearest star, lies 4.25 light-years away, approximately 25 trillion miles. This means the light we see from it tonight began its journey more than 4 years ago. Our fastest spacecraft would take tens of thousands of years to reach it. Already, we're stretching the limits of comprehension. But we've barely begun our cosmic scaling. The Milky Way galaxy, our home in the universe, spans roughly 100,000 light-years across, a distance so vast that light itself, the cosmic speed limit, takes 100 millennia to cross it. Our solar system occupies a tiny region in one spiral arm of this vast stellar city. If the entire Milky Way were reduced to the size of North America, our solar system would be smaller than a coffee cup. We are cosmically microscopic. Within this galactic expanse reside between 100 to 400 billion stars, many with their own planetary systems. Recent discoveries suggest that planets may be common throughout the galaxy, with potentially billions of Earth-like worlds among them. Yet even this immense collection of stars is merely one island universe in a cosmos teeming with galaxies. The nearest major galaxy to our own, Andromeda, lies 2.5 million light-years distant, a gap 25 times wider than the entire Milky Way. To visualize this, if we shrink the Milky Way down to the size of a dinner plate, Andromeda would be another plane about 25 feet away. Between them would be mostly empty space, with only a few scattered dwarf galaxies like cosmic dust motes. The local group, our galactic neighborhood, contains about 80 galaxies dominated by the Milky Way and Andromeda. This entire collection spans roughly 10 million light-years, a cosmic community bound together by gravity across unimaginable distances. Beyond our local group lies the Virgo cluster, a collection of about 1,500 galaxies, approximately 54 million light-years away. And beyond that, superclusters, massive agglomerations of galaxy clusters stretching across hundreds of millions of light-years. The observable universe, the cosmic horizon beyond which we cannot see due to the finite age of the universe and the speed of light, extends roughly 93 billion light-years in diameter. Within this sphere exist approximately 2 trillion galaxies. Each of these measurements represents not just distance but time. When astronomers observe a galaxy 100 million light-years away, they see it as it was 100 million years ago, when dinosaurs still roamed the Earth, long before humans existed. The most distant galaxies visible through our most powerful telescopes appear as they were more than 13 billion years ago, when the universe was young and the first stars were just beginning to shine. We see cosmic history spread before us in space and time. Against this backdrop of cosmic scale, the challenge of intergalactic travel comes into sharper focus. Even reaching the nearest star within our galaxy presents formidable obstacles. Crossing the void to another galaxy multiplies these difficulties by orders of magnitude. Consider the energy required. Using our current chemical rocket technology to send even a small probe to Alpha Centauri would require more fuel than exists on Earth. The rocket equation, which relates mass, propellant, and velocity, becomes exponentially prohibitive. More advanced propulsion concepts exist, at least theoretically. Nuclear pulse propulsion, essentially riding the shock waves from a series of nuclear explosions, could potentially achieve up to 10% the speed of light, cutting travel time to Alpha Centauri to about 40 years. Light sails powered by massive Earth-based lasers represent another possibility. The Breakthrough Starshot initiative aims to develop gram-sized probes attached to light sails that could be accelerated to 20% the speed of light, reaching Alpha Centauri in about 20 years. But even these speculative technologies, if successful for interstellar travel, fall woefully short for intergalactic journeys. At 20% light speed, reaching Andromeda would still take 12.5 million years, longer than the entire evolutionary history of the human species. The challenges extend beyond mere distance. Interstellar space contains tenuous gas and dust that would impact any fast-moving spacecraft with tremendous energy. At relativistic speeds, even individual hydrogen atoms become dangerous projectiles. Radiation presents another hazard. Cosmic rays, high-energy particles from distant supernova and other cosmic events, permeate space. Earth's magnetic field and atmosphere shield us from most of this radiation, but spacecraft would need substantial protection. For crewed missions, the biological challenges multiply. Humans require not just air, food, and water, but also protection from microgravity's detrimental effects on bones, muscles, and cardiovascular systems. These effects compound over long durations. The psychological impacts of such journeys would be equally profound. Imagine a spacecraft departing our galaxy with a crew knowing they would never see home again, that countless generations would live and die aboard their vessel before reaching their destination. Even communication becomes problematic at these distances. Radio signals, traveling at light speed, would take millions of years to reach Earth from an intergalactic vessel. Any message sent home would arrive in a world where human civilization might no longer exist. Some theorists have proposed generation ships, essentially mobile worlds where people would live entire lives during the journey, with only distant descendants reaching the destination. Such vessels would need to function as self-sustaining ecosystems for millennia. Others speculate about suspended animation or human hibernation, technologies that might allow travelers to essentially skip forward through time during the journey. But even these approaches face the fundamental limitation of light speed and cosmic distance. More exotic possibilities emerge from theoretical physics. Einstein's equations allow for the existence of wormholes, hypothetical tunnels through space-time that could connect distant points. However, creating and stabilizing such structures would require negative energy and exotic matter. Similarly, the Alcubierre warp drive, a theoretical concept that would compress space-time in front of a vessel while expanding it behind, might allow effective faster-than-light travel without violating relativity. But its energy requirements exceed all available energy in the observable universe. As we stand at the precipice of our first section, gazing across the cosmic ocean toward distant galactic shores, we must confront a profound question. Are the laws of physics as we understand them absolute barriers to intergalactic travel, or merely challenges awaiting future solutions? The most honest answer lies somewhere between sobering reality and cautious optimism. The barriers are immense, perhaps insurmountable for biological humans as we currently exist. Yet the history of science teaches us humility about declaring anything absolutely impossible. What we can say with certainty is this: reaching another galaxy represents the ultimate challenge for our species. A journey so vast that it would require technologies beyond our current comprehension and patience beyond our evolutionary programming. In our next section, we'll explore what these harsh realities mean for humanity's future, examining potential pathways that might, against all odds, eventually allow us to touch those distant shores of space and time. Chapter 5: Contradictions and Anomalies. The universe rarely fits neatly into our conceptual frameworks. As we deepen our exploration of intergalactic travel, we encounter curious contradictions and anomalies that challenge our understanding. These puzzles may hold keys to possibilities beyond our current scientific horizons. Consider first the cosmic speed limit established by Einstein's theories of relativity. This seemingly insurmountable barrier, the speed of light, appears to render intergalactic travel practically impossible. Yet the same theories that establish this limit also reveal intriguing loopholes. Einstein's equations don't actually forbid faster-than-light travel. They only prohibit accelerating through the light barrier. This subtle distinction has led theoretical physicists to explore concepts like wormholes and warp drives that could potentially bypass the speed limit without violating it. The mathematics supporting these exotic possibilities is sound, derived directly from general relativity. The contradiction emerges not from the theory itself, but from the physical requirements: negative energy and exotic matter that may not exist, or may be impossible to harness. Yet history teaches us caution when declaring anything impossible. Telecommunications, nuclear energy, and space travel were all once considered beyond reach. Our understanding of fundamental physics continues to evolve, sometimes in revolutionary ways. Dark energy presents another cosmic anomaly with potential implications for intergalactic travel. This mysterious force, driving the accelerated expansion of the universe, contradicts our intuitive understanding of gravity and comprises roughly 68% of the universe's total energy content. Yet we know almost nothing about its fundamental nature. Some theoretical models propose that dark energy might be manipulated to create negative pressure regions of spacetime, exactly what would be needed for certain faster-than-light propulsion concepts. The quantum realm offers additional contradictions to our classical understanding. Quantum entanglement allows particles to influence each other instantaneously across any distance, seemingly violating the light speed limit. Einstein himself called this spooky action at a distance. While current understanding suggests this quantum connection cannot transmit useful information faster than light, the boundaries between quantum mechanics and general relativity remain poorly understood. The reconciliation of these theories may reveal new possibilities. Some theoretical physicists have proposed that certain quantum effects might enable the creation of traversable wormholes, shortcuts through spacetime that could connect distant regions of the universe. Recent calculations suggest these might require less exotic matter than previously thought. In 2017, physicists at the University of Cambridge and Queen Mary University of London published work suggesting that wormholes might be constructed without negative energy, using only conventional matter and electromagnetic fields arranged in specific configurations. Meanwhile, plasma physicist Harold White, formerly with NASA, has conducted experiments attempting to detect microscopic distortions in spacetime that might validate aspects of the Alcubierre warp drive theory. While preliminary and controversial, such work explores theoretical boundaries. Another anomaly emerges from our increasing understanding of the cosmos structure. Galaxies are not distributed uniformly, but form vast filaments and sheets with enormous voids between them. This cosmic web creates a landscape where some intergalactic distances are significantly shorter than others. If we imagine the universe as a sponge, galaxies cluster along the solid portions, with relatively empty spaces between. Strategic routes through this cosmic structure could potentially reduce travel distances by billions of light years compared to straight-line paths. The expanding nature of the universe presents yet another contradiction relevant to intergalactic travel. While cosmic expansion increases distances between galaxies over time, it also creates situations where certain destinations might become permanently unreachable. Galaxies beyond a certain distance are receding faster than light due to cosmic expansion, not because they're violating physics, but because space itself is stretching. This cosmic horizon means that even with theoretical faster-than-light technology, portions of the universe would remain forever beyond our reach. This sobering reality suggests a timetable. If humanity ever hopes to explore the broader universe, sooner is better than later. Every passing eon places more of the cosmos permanently beyond potential contact, an urgency that contradicts the seemingly limitless time ahead. Recent astronomical observations have revealed another puzzling phenomenon. Some galaxies appear to be moving through space at speeds far greater than expected. These hypervelocity galaxies challenge our understanding of cosmic mechanics and energy transfer. In 2017, astronomers discovered a galaxy moving at approximately 8% of light speed, far faster than standard cosmic expansion would explain. Such anomalous motion hints at complex gravitational interactions or other forces that might someday be understood and potentially harnessed. Contradictions also emerge when we consider the biological aspects of intergalactic travel. Human bodies evolve for Earth conditions and lifespans measured in decades. Yet some extremophile organisms on Earth demonstrate surprising radiation resistance and suspended animation capabilities. Tardigrades, microscopic aquatic animals, can survive in space, endure radiation levels thousands of times what would kill humans, and enter cryptobiosis, a state of nearly suspended metabolism for decades. Such biological adaptability suggests possibilities for life beyond Earth's parameters. Recent advances in genetic engineering raise profound questions about the future boundaries between human and technology. If consciousness could someday exist within engineered substrates designed for deep space conditions, would biological limitations still constrain our cosmic reach? This intersection of biology and technology creates a contradiction in our thinking about space travel. We imagine humans as they currently exist traveling to other galaxies, when perhaps the question should be, how might humanity transform itself to become suited for such journeys? Time perception itself presents another fascinating contradiction. Einstein's relativity tells us that time is relative. It passes differently depending on gravity and velocity. At speeds approaching light, time dilation becomes extreme, potentially making even vast journeys subjectively brief. A spacecraft traveling at 99.999% the speed of light would experience profound time compression. For the travelers, a journey to Andromeda might take only a few months of subjective time, while millions of years pass for those left behind, a solution and a tragedy simultaneously. Some physicists have speculated about even more exotic possibilities. In certain interpretations of quantum mechanics, particularly the many worlds hypothesis, reality branches with each quantum event. This raises a mind-bending question. Could intergalactic travel involve quantum transitions between parallel realities? If consciousness could somehow navigate or influence these quantum branches, might there be paths where the gap between galaxies is dramatically different? This speculation remains far beyond current science, but illustrates how foundational physics questions connect to our cosmic ambitions. Anomalies in cosmic ray observations offer another puzzle piece. Ultra-high energy cosmic rays impact Earth's atmosphere, carrying energies millions of times greater than our most powerful particle accelerators can produce. Their origin remains mysterious, as does their acceleration mechanism. If we could understand and replicate whatever natural process accelerates these particles to 99.9999999% of light speed, we might gain crucial insights into high-efficiency propulsion technologies that could dramatically reduce intergalactic travel times. A final contradiction worth considering is philosophical. The vast distances between galaxies seem to render physical travel between them impossible. Yet we can observe, study, and in a sense, visit them through our telescopes. Our consciousness already bridges intergalactic space, even if our bodies cannot. This distinction between physical presence and observational knowledge raises profound questions about the nature of exploration itself. Perhaps the future of intergalactic connection lies not in physically transporting human bodies, but in developing new ways of extending perception and consciousness. As we navigate these contradictions and anomalies, we should remember that the history of science is a story of expanding boundaries. What seems impossible today may become achievable tomorrow, not because the laws of physics change, but because our understanding of them deepens. Chapter 6. Myths, Misreads, and Edge Cases. The vast scales and exotic physics involved in intergalactic travel have spawned numerous myths and misconceptions. Some arise from genuine misunderstandings of complex science, others from science fiction's creative liberties, and still others from our deep human desire to transcend our limitations. Perhaps the most pervasive myth is that NASA or other space agencies are actively developing warp drive technology based on the Alcubierre equations. Headlines occasionally announce NASA's warp drive or claim faster than light travel coming soon, dramatically overstating preliminary theoretical explorations. The reality is more nuanced. While NASA's Eagle Works laboratory has conducted some speculative research into advanced propulsion concepts, these represent thought experiments and theoretical calculations, not practical engineering projects with any near-term application. A related misconception involves the energy requirements for theoretical warp drives. Early calculations suggested they would require more energy than exists in the observable universe. While newer models have reduced these estimates, they remain far beyond our technological capabilities. Even the most optimistic revised calculations would require energy equivalent to converting the entire mass of Jupiter into pure energy, a feat well beyond our current or foreseeable technological horizon, requiring perfect matter-antimatter conversion on a planetary scale. Another common misread concerns Einstein's theories of relativity. Popular articles sometimes claim Einstein proved nothing can travel faster than light, overlooking the nuance that his theories actually state. Nothing can accelerate through the light-speed barrier within normal spacetime. This distinction matters because it leaves theoretical room for phenomena like wormholes or space warping, which don't involve conventional acceleration through space, but rather alter the structure of space-time itself. These remain highly speculative, but aren't explicitly forbidden by relativity. Science fiction has given us the gift of imagining cosmic possibilities, but it has also created persistent myths. The hyperspace or jump to light speed, portrayed in popular media, suggests intergalactic travel might be as simple as pressing a button once the technology is developed. The reality is that any practical interstellar, let alone intergalactic propulsion system would involve complex trade-offs between energy requirements, travel time, and payload mass. There is no foreseeable technology that would make such journeys casual or convenient. Another misconception involves alien visitation. Some suggest that extraterrestrial civilizations must have overcome these immense distances to visit Earth. While the existence of extraterrestrial intelligence remains an open scientific question, the physics of intergalactic travel applies to all civilizations. Any civilization, no matter how advanced, would face the same fundamental constraints of energy, time, and physical law that we do. If intergalactic travel proves extraordinarily difficult for fundamental reasons, it would be difficult for everyone, not just for humans. A persistent myth surrounding black holes suggests they might serve as natural wormholes or cosmic shortcuts. While mathematically, certain black hole solutions do connect to white holes in other regions of spacetime, there's no evidence that actual black holes function this way. Moreover, the intense tidal forces near a black hole's event horizon would tear apart any physical object long before it could utilize any theoretical passage. The popular image of black holes as cosmic tunnels remains firmly in the realm of science fiction. Some edge cases do exist at the boundaries of our understanding. Quantum entanglement, for instance. Those appear to allow for instantaneous correlation between particles regardless of distance. This spooky action at a distance, as Einstein called it, seems to violate locality principles. However, careful analysis shows that entanglement cannot transmit usable information faster than light. The correlation exists but cannot be used for practical communication or transportation across cosmic distances without a conventional, light-speed limited classical channel. Another misunderstood concept is the expansion of the universe. Some suggest we might ride cosmic expansion to distant galaxies. But expansion primarily affects the space between galaxy clusters, not the space within our local group or between nearby galaxies. Additionally, cosmic expansion isn't a force that can be harnessed for propulsion. It's a property of spacetime itself. Objects aren't moving through space due to expansion. Rather, the space between them is increasing. This isn't something a spacecraft could utilize. The concept of generation ships, vast self-contained habitats where multiple generations would live and die during an interstellar journey, represents an edge case worth examining. While technically feasible for interstellar journeys, the social and psychological challenges would be enormous. For intergalactic voyages lasting millions of years, the concept stretches beyond reasonable limits. Human societies rarely maintain continuity of purpose across even a few centuries. The likelihood of maintaining mission focus across thousands of generations approaches zero. Some futurists propose mind uploading or digital consciousness as a solution to biological limitations. If human minds could be transferred to robotic or virtual substrates, the biological constraints of time and radiation exposure might be overcome for long-duration space missions. This represents an intriguing edge case, but one that assumes consciousness is fully transferable to non-biological systems, a proposition that remains deeply controversial in neuroscience and philosophy of mind, with no clear path to practical implementation. A related misconception involves suspended animation or cryonic preservation. While certain organisms can enter states of drastically reduced metabolism, and medical science can briefly induce therapeutic hypothermia, true human hibernation for centuries or millennia remains speculative. The challenges include preventing cell damage during freezing, maintaining biological systems during prolonged dormancy, and the ethical questions of launching humans on one-way journeys to destinations they may never reach if the technology fails or civilization collapses. Some popular articles suggest that quantum physics might eventually allow for teleportation across cosmic distances. While quantum teleportation is a real phenomenon, it doesn't work the way science fiction portrays it. It transfers quantum states, not physical matter or energy. Moreover, quantum teleportation requires both a quantum channel and a classical communication channel. The classical channel is limited by the speed of light, meaning that even perfect quantum teleportation technology couldn't exceed Einstein's cosmic speed limit. An edge case worth considering involves von Neumann probes, self-replicating robotic systems that could theoretically build copies of themselves from raw materials on distant worlds. These might spread across a galaxy without requiring individual craft to travel the full distances. For intergalactic exploration, such systems might eventually establish presence in other galaxies, though the initial crossing would still require millions of years. This represents a potential solution for robotic exploration, though not for human intergalactic travel. A persistent misread involves the timescales of technological development. Some suggest that if we extrapolate from the dramatic advances of the past century, surely we'll develop practical intergalactic travel within a few more centuries or millennia. This ignores the difference between engineering challenges and fundamental physical constraints. While technology has advanced rapidly in many areas, the speed of light and the vast cosmic distances represent constraints of an entirely different order. Some coverage of breakthrough propulsion physics misrepresents theoretical work as practical engineering. The M drive, for example, generated headlines suggesting it might revolutionize space travel, despite questionable experimental results and theoretical foundations that most physicists find dubious. Cosmic strings represent another edge case occasionally cited as potential faster-than-light enablers. These hypothetical one-dimensional defects in spacetime might, if they exist, create closed time-like curves that could theoretically allow for effective FTL travel or communication. However, most theoretical physicists believe that even if cosmic strings exist, the universe likely enforces a chronology protection conjecture that prevents the creation of time machines or causality violations, closing this potential loophole in relativistic physics. The scales involved in intergalactic travel often lead to numerical misreads in popular coverage. Headlines might declare a breakthrough making travel to other stars possible within a human lifetime, neglecting to clarify that this refers only to our nearest stellar neighbors. Even if we develop technology that could reach Alpha Centauri in 40 years, reaching Andromeda would still take 2.5 million years. The difference between interstellar and intergalactic travel is not one of degree, but of kind, a gulf of several orders of magnitude. A final myth worth addressing involves alien megastructures. Occasional astronomical observations of unusual light patterns from distant stars spawn speculation about advanced civilizations building Dyson spheres or similar energy-capturing structures around their stars. While the search for technosignatures represents legitimate science, the leap from unusual observations to conclusions about alien engineering projects represents a form of extraordinary claims require extraordinary evidence, reasoning failure that permeates discussions of cosmic possibilities. As we navigate these myths and edge cases, maintaining a balance between wonder and skepticism serves us best. The cosmos may indeed hold possibilities beyond our current understanding, but the most remarkable journey may be the one our collective knowledge takes as we explore these boundaries. Chapter 7: Stakes and What Changes If True. What exactly is at stake in our quest to understand the possibilities of intergalactic travel? Beyond scientific curiosity, the implications touch on humanity's long-term survival, our cosmic perspective, and the very meaning we assign to our existence in this vast universe. Perhaps the most immediate stake involves our understanding of cosmic isolation. If the harsh reality of physics truly prohibits practical travel between galaxies, humanity's future, however long it might extend, will be confined to our local group of galaxies. This isolation has profound implications. As the universe continues expanding, galaxies beyond our local group will eventually recede beyond any possibility of contact. The cosmic horizon will close in, limiting even our ability to observe those distant shores. Within a few trillion years, observers in the Milky Way, by then merged with Andromeda, will see only darkness beyond our local galactic neighborhood. The evidence of the Big Bang and the larger cosmic structure will fade from view, altering how future civilizations understand their context. This cosmological isolation represents a kind of ultimate quarantine, not just for humans, but potentially for all life in the universe. Different galactic neighborhoods would become permanently disconnected islands, each with its own cosmic fate and evolutionary trajectory. If, however, we discovered a viable method of intergalactic travel, perhaps through a fundamental breakthrough in physics, the stakes would shift dramatically. Humanity's potential sphere of influence could expand beyond our galactic borders, opening vast new frontiers. Such a breakthrough would likely revolutionize our understanding of physics itself. The energy manipulation required for intergalactic travel would transform every aspect of human civilization, from energy production to computing, medicine, and environmental management. Consider the implications for long-term human survival. Earth faces numerous existential threats: asteroid impacts, supervolcanic eruptions, and eventually the sun's expansion. Expanding beyond our solar system represents a crucial insurance policy against extinction. But galactic-scale threats also exist. In roughly 4 billion years, the Milky Way will collide with Andromeda. While individual star collisions will be rare, the gravitational disruption could potentially destabilize our solar system or expose Earth to increased radiation. On even longer timescales, galaxies will experience heat death as stars exhaust their fuel and no new stars form. Intergalactic travel capabilities might allow a sufficiently advanced civilization to migrate to younger galaxies with more abundant resources and energy. The philosophical stakes are equally profound. Our cosmic perspective fundamentally shapes how we understand ourselves. The apparent impossibility of reaching other galaxies reinforces a sense of cosmic humility. We are bound to our corner of the universe. This perspective can foster greater appreciation for Earth and our solar system as our only viable home. If we can never reach other galaxies, then preserving the habitability of the worlds we can reach becomes an imperative of the highest order. Conversely, if intergalactic travel proves possible, our self-conception as a species would undergo a radical transformation. Humanity would need to reimagine itself as potentially pan-galactic, with all the responsibility and perspective shifts such a status would entail. The cultural impacts would be equally significant. Throughout history, the discovery of new horizons has profoundly influenced art, religion, philosophy, and social structures. Opening a truly cosmic frontier would likely spark cultural transformations we can barely imagine. One of the most fascinating stakes involves the search for extraterrestrial intelligence. If intergalactic travel is fundamentally impossible due to physics, it would help explain the Fermi paradox, the question of why, in a seemingly vast and ancient universe, we detect no signs of other civilizations. The harsh reality of cosmic distances might mean that intelligent life remains perpetually isolated in separate galactic islands, unable to establish contact across the intergalactic void. Each technological civilization might be effectively alone, regardless of how many others exist. If, however, intergalactic travel is possible through physics we don't yet understand, the absence of visitors becomes more puzzling. It would suggest either that advanced civilizations are exceedingly rare, that they choose not to travel widely, or that they remain deliberately hidden. The scientific stakes extend to our understanding of consciousness itself. If physical human travel between galaxies proves impossible, might we develop other ways of extending our presence? Perhaps through advanced quantum entanglement or technologies we cannot yet conceive. This raises profound questions about what constitutes travel or presence. If we could somehow project consciousness or information across intergalactic distances without moving physical bodies, would this satisfy our exploratory urge? Would it count as truly being there? For astronomy and cosmology, the implications are equally transformative. Our understanding of the universe currently depends entirely on observation from Earth or nearby space. Direct sampling and in situ measurement in other galaxies would revolutionize our cosmic knowledge. Imagine studying star formation in galaxies with different chemical compositions, directly observing supermassive black holes in galactic centers, or investigating whether the laws of physics themselves might vary subtly across cosmic distances. Such capabilities would transform science. The engineering challenges of intergalactic travel would drive innovation across all fields. Even pursuing this seemingly impossible goal would likely produce technological spin-offs with immense benefits, just as the space race yielded advances from computing to material science. On timescales of millions or billions of years, cosmic events become relevant to humanity's fate. Gamma-ray bursts, galaxy collisions, and vacuum decay could potentially threaten entire galactic regions. True long-term survival might require the ability to migrate between galaxies. If humanity or its descendants eventually achieve such capability, our cosmic ethical responsibilities would expand accordingly. How should an intergalactic species interact with potentially life-bearing worlds in other galaxies? What principles should guide such contact? The preservation of cosmic biodiversity might become an ethical imperative. If life proves rare, a species capable of intergalactic travel might assume responsibility for preserving and perhaps even spreading life's potential throughout the cosmos. Meanwhile, the harsh reality of our current technological limitations demands that we focus on more immediate horizons. Before contemplating jumps between galaxies, we must first develop sustainable presence throughout our solar system and eventually reach nearby stars. This creates a nested set of challenges, each preparing us for the next. Learning to live sustainably on Mars or in space habitats develops the closed system ecological understanding needed for longer journeys. Each step builds capacity for the next horizon. The timescales involved also force us to confront questions of species continuity and identity. If a journey takes millions of years, would those who arrive still be human in any meaningful sense? Would they retain connection to their terrestrial origins? Evolution, whether natural or self-directed, would likely transform any traveling population over such vast periods. The descendants who might eventually reach another galaxy could be as different from us as we are from our earliest mammalian ancestors. This raises a profound question. Is the goal of reaching other galaxies something that we, as currently constituted humans, can meaningfully pursue? Or is it more accurately described as a project we might initiate for descendants who will barely resemble us? What remains constant across these considerations is the human impulse to explore, to know, to touch the unknown. Whether or not we ever physically reach another galaxy, the quest to understand how we might do so expands our perspective and capabilities. The pursuit itself, regardless of its physical achievement, transforms us. In contemplating these vast distances and challenges, we develop new technologies, new philosophies, and new understandings of our place in the cosmos. Perhaps most importantly, grappling with these questions helps us appreciate the remarkable accident of our existence. We are conscious beings who evolved on a rocky planet orbiting an average star in an ordinary galaxy. yet we can contemplate journeys across billions of light years. This cognitive leap, from our modest biological origins to contemplating intergalactic travel, represents perhaps the most extraordinary journey our species has already undertaken. It speaks to something remarkable about consciousness itself. As we approach the final section of our exploration, we face a crucial question. Given the harsh realities of physics as we currently understand them, what paths forward remain available? Are there approaches to cosmic connection that transcend the physical limitations we've identified? The answers may lie not in conventional propulsion or even exotic physics, but in reimagining what exploration means in a quantum universe. The boundaries between observation, information, consciousness, and physical presence may prove more fluid than we currently understand. In our next section, we'll explore the most promising approaches to this seemingly intractable problem, examining cutting-edge physics, speculative technologies, and philosophical perspectives that might offer pathways, if not to physical intergalactic travel, then to new forms of cosmic connection. Chapter 8. Strongest competing theories. As we approach the culmination of our journey, we must consider the most viable theoretical approaches to the seemingly insurmountable challenge of intergalactic travel. Three compelling frameworks have emerged, each with profound implications for our cosmic future. The first framework might be called generational transcendence. It accepts the fundamental constraints of physics as we currently understand them, but proposes that over millions of years, a determined civilization might gradually expand outward through conventional means. This approach envisions a patient, multi-stage expansion, first throughout our solar system, then to nearby stars, eventually spreading throughout the Milky Way using sublight propulsion technologies advanced beyond our current capabilities, but not breaking fundamental physical laws. Once established across our galaxy, humanity's descendants might launch specialized vessels toward Andromeda, knowing the journey would take millions of years. These arc ships would carry either hibernating biological beings, digital consciousnesses, or self-replicating systems. The generational transcendence model doesn't require new physics, merely the consistent application of technologies we can already conceptualize: fusion propulsion, suspended animation, artificial habitats, and potentially uploaded consciousness or artificial intelligence. Its primary strength lies in its compatibility with established physics. Its weakness is the almost incomprehensible timescale required. Millions of years of continuous technological civilization, maintaining focus on a single goal across countless generations. The second framework, space-time engineering, suggests that sufficiently advanced civilizations might manipulate the fabric of space-time itself, potentially creating shortcuts between distant regions of the cosmos through artificial wormholes or Alcubierre-type warp bubbles. While speculative, this approach derives from legitimate solutions to Einstein's field equations. Theoretical physicist Kip Thorne and others have shown that certain wormhole configurations could, in principle, allow for travel between distant points without violating local physics. Recent theoretical work has reduced the estimated energy requirements for such systems from impossible to merely extraordinarily difficult. Some calculations suggest that a negative energy equivalent to the mass energy of Jupiter might create a traversable wormhole. The primary strength of the space-time engineering approach is that it offers a potential way around the light-speed barrier without actually breaking it. Its weakness lies in the extraordinary technical challenges and the requirement for exotic matter or energy states. Both approaches maintain a common assumption: that consciousness must be tied to some physical substrate, whether biological or technological, that must physically traverse the vast distances between galaxies. But a third framework challenges this fundamental premise. This third approach might be called consciousness transcendence. It proposes that advanced civilizations might eventually transcend the need for physical travel altogether, instead developing means to extend consciousness, observation, or influence across cosmic distances, rather than moving physical bodies between galaxies. This model envisions transferring information, creating entangled systems, or developing entirely new forms of awareness that aren't constrained by traditional notions of location and physical presence. Some theoretical physicists have speculated that consciousness itself may have quantum properties. If so, and if those properties interact with quantum fields that extend throughout the universe, there might be pathways to cosmic awareness we cannot yet conceive. Recent experiments with quantum entanglement demonstrate spooky action at a distance, where particles maintain instantaneous correlations regardless of separation. While this cannot currently transmit information faster than light, it hints at non-local connections in nature. The consciousness transcendence model's strength lies in its recognition that our understanding of consciousness remains incomplete. Its weakness is its highly speculative nature and the risk of veering from physics into metaphysics without empirical grounding. Each of these frameworks contains elements of both science and speculation, existing at the boundary of what we know and what we can imagine. None offers a guaranteed path to intergalactic connection, but each suggests possibilities worth exploring. It's worth noting that these approaches need not be mutually exclusive. A long-term strategy might involve pursuing all three simultaneously: conventional expansion throughout our galaxy, research into space-time engineering, and exploration of consciousness and its relationship to physics. The generational transcendence approach offers the clearest path forward based on known physics. Even if intergalactic travel proves impossible, establishing a presence throughout our own galaxy would represent an extraordinary achievement and insurance policy for humanity's future. The space-time engineering approach, while more speculative, connects to ongoing research in quantum gravity and other advanced physics. Even if artificial wormholes prove impractical, the pursuit may yield profound insights into the nature of space-time. The consciousness transcendence approach, no furthest from current scientific consensus, aligns with humanity's historical pattern of redefining problems rather than merely solving them as initially framed. Perhaps being there might eventually mean something different than physical presence. What unites these frameworks is the recognition that intergalactic connection, if it happens at all, represents an ultra-long-term project for our species. It would unfold not over years or decades, but over millennia and perhaps millions of years. This extended timescale forces us to consider questions of species continuity. Would the beings who eventually reach another galaxy still be human in any meaningful sense? Or would they have evolved, naturally or through technological self-modification, into something else entirely? Perhaps the most realistic perspective acknowledges that if intergalactic travel ever occurs, it will be achieved not by humans as we currently exist, but by our descendants so advanced that we might not recognize them as related to us at all. This realization doesn't render the question irrelevant but shifts its framing. We may be asking not, can humans reach other galaxies? But rather, can we initiate a process that might eventually lead to some form of consciousness with terrestrial origins reaching other galaxies? From this perspective, our current scientific explorations, technological developments, and philosophical inquiries might be seen as the earliest foundations for a project that could extend millions of years into the future, a truly intergenerational endeavor. Each of these frameworks contains profound implications, not just for potential intergalactic travel, but for how we understand ourselves and our place in the cosmos. They invite us to consider human potential across timeframes that dwarf our ordinary thinking. As we contemplate these competing theories, we must remember that throughout history, the most profound scientific revolutions have often emerged not from incremental advances within existing paradigms, but from fundamental shifts in how we conceptualize problems. Perhaps the ultimate solution to intergalactic travel will come not from building faster ships or more efficient propulsion systems, but from a completely reimagined relationship between consciousness, information, and the physical universe, a paradigm we can barely glimpse from our current vantage point. Chapter 9: New Science, Instruments, and Paradoxes. Our understanding of cosmic distances and the possibilities for traversing them continues to evolve as new scientific instruments and methodologies extend our perceptual reach. These technological advances don't just improve existing measurements, they sometimes reveal entirely new aspects of reality. The James Webb Space Telescope, JWST, launched in 2021, represents a quantum leap in our ability to observe distant galaxies. Operating primarily in the infrared spectrum, it can peer through cosmic dust clouds that obscure visible light, revealing galaxy formation in unprecedented detail. JWST's capabilities allow astronomers to study galaxies as they appeared just a few 100 million years after the Big Bang. By examining these earliest galactic structures, we gain insights into the fundamental processes that govern galaxy formation and evolution. This deep historical view provides crucial context for understanding intergalactic space. The early universe was much more compact, with galaxies closer together. As cosmic expansion continues, intergalactic distances increase, making the challenge of crossing them more difficult with each passing eon. Another revolutionary instrument, the Event Horizon Telescope, EHT, recently captured the first images of supermassive black holes at the centers of galaxies. These observations confirm a key prediction of Einstein's general relativity, that sufficient mass can dramatically warp spacetime. This empirical verification of extreme spacetime curvature has important implications for theoretical approaches to intergalactic travel. If natural processes can create such dramatic warping, perhaps advanced technologies might someday manipulate spacetime in less extreme but still useful ways. The Laser Interferometer Gravitational Wave Observatory, LIGO, has opened an entirely new window on the cosmos by detecting gravitational waves, ripples in spacetime created by violent cosmic events like colliding black holes and neutron stars. LIGO's success confirms another prediction of general relativity, that space itself can ripple like the surface of a pond. This empirical validation of spacetime's dynamic nature provides crucial foundation for theoretical work on artificial spacetime manipulation. Meanwhile, neutrino observatories buried deep underground or in Antarctic ice detect nearly massless particles that travel at almost the speed of light and barely interact with ordinary matter. These ghostly particles carry information across the universe with minimal disruption. The study of neutrinos offers potential insights into fundamental physics that might eventually inform advanced propulsion concepts. Their ability to traverse cosmic distances with minimal interaction suggests possibilities for communication, if not transportation, across intergalactic voids. Gravitational lensing, where massive objects bend light from more distant sources, allows astronomers to observe galaxies that would otherwise be too distant or faint to detect. This natural cosmic magnifying glass extends our observational reach billions of light years into the universe. By studying these gravitationally lensed galaxies, we can better understand the distribution of matter, both visible and dark, throughout intergalactic space. This improved mapping of the cosmic landscape could theoretically identify optimal paths for any future intergalactic ventures. The European Extremely Large Telescope, ELT, currently under construction in Chile, will become the world's largest optical telescope when completed. With a primary mirror 39 meters in diameter, it will collect 13 times more light than any existing telescope. This unprecedented light-gathering capacity will allow direct imaging of exoplanets in nearby star systems and detailed study of galaxies across cosmic time. It may reveal aspects of galactic structure and evolution that remain hidden from even our current best instruments. Beyond these observational advances, theoretical physics continues to probe the fundamental nature of reality. Quantum mechanics and general relativity, our two most successful physical theories, remain stubbornly incompatible, suggesting deeper principles we have yet to discover. Attempts to reconcile these frameworks have spawned various approaches to quantum gravity: string theory, loop quantum gravity, causal set theory, and others. Though still speculative, these theories hint at a deeper understanding of space-time that could eventually inform intergalactic travel concepts. Recent laboratory experiments with quantum entanglement continually push the boundaries of our understanding. In 2022, researchers demonstrated entanglement between particles separated by more than 10 miles, with correlations that appear instantaneous, challenging our intuitions about space and time. While current understanding suggests these quantum correlations cannot transmit useful information faster than light, the expanding experimental verification of quantum non-locality hints at aspects of reality that transcend our conventional understanding of spatial separation. Advanced computer simulations now model galaxy formation and evolution with unprecedented detail. These computational approaches reveal the complex interactions between dark matter, ordinary matter, and the cosmic web, improving our understanding of intergalactic structure. Such simulations might eventually help identify natural highways through intergalactic space, regions where cosmic expansion, gravitational effects, or other factors might make certain paths between galaxies more favorable than others for hypothetical future travelers. Paradoxically, as our instruments reveal more about the universe, they often deepen rather than resolve its mysteries. The accelerating cosmic expansion discovered in the late 1990s revealed dark energy, an unknown force that comprises roughly 68% of the universe's total energy content. The nature of this dark energy remains one of physics' greatest unsolved puzzles. Some speculative theories suggest it might relate to properties of the quantum vacuum or represent a fifth fundamental force. Understanding it could conceivably open new approaches to manipulating spacetime. Similarly, dark matter, which accounts for about 27% of the universe's mass energy, remains undetected except through its gravitational effects. As we develop new technologies to study these invisible components, we may gain insights that fundamentally change our understanding of what's possible. These unknowns remind us that we're still in the early stages of cosmic understanding. Just as seafarers once believed that the edge of the known world represented absolute limits, our current conception of physical limitations may someday be viewed as quaint misconceptions. Another paradox emerges from cosmological constants, fundamental numbers that govern the universe's basic properties. Many appear suspiciously fine-tuned to allow for complex structures like galaxies, stars, and ultimately life. This has led to multiverse theories suggesting our universe may be one of many. If the multiverse concept proves correct, it would profoundly impact how we think about intergalactic travel. Perhaps the ultimate journey wouldn't involve crossing our universe's vast gulfs, but somehow accessing parallel universes with different physical laws or spatial configurations. Advances in material science continue to produce substances with properties that would have seemed magical to earlier generations. Metamaterials that bend light in impossible ways, room temperature superconductors, and quantum materials with behaviors that challenge classical intuition. While no material can directly enable faster-than-light travel, these advances expand our conception of what's physically possible. They remind us that nature contains possibilities beyond our current imagination, accessible only through persistent scientific inquiry. Meanwhile, astrobiology and the search for extraterrestrial intelligence, SETI, provide a complementary perspective. If other technological civilizations exist, they would face the same intergalactic travel challenges we do. Their solutions, or lack thereof, might inform our understanding. Recent advances in detecting biosignatures and technosignatures might someday reveal whether other civilizations have attempted interstellar or intergalactic journeys. Evidence of ancient probes or artifacts could provide crucial data points about the feasibility of such ventures. As our instruments grow more sensitive and our theories more sophisticated, we continue to push against the boundaries of the known. Each advance reveals new puzzles, suggesting that our cosmic journey of discovery has only just begun. Chapter 10. The Big Reveal. Throughout our journey, we've explored the vast distances between galaxies, the physical constraints on travel, and the theoretical possibilities that might someday allow us to bridge these cosmic gulfs. Now we must confront our central question directly. What happens if you try to reach another galaxy? The answer, like many profound truths, contains both harshness and beauty. Based on our current understanding of physics, biology, and cosmology, the harsh reality is this: physical human travel to another galaxy is effectively impossible within the constraints of human lifespans and known physics. The distances are simply too vast, the energy requirements too enormous, and the timescales too extended for biological humans as we currently exist to make such a journey. Even at 99% of light speed, the trip to Andromeda would take 2.5 million years. No technology currently on our horizon can meaningfully compress this journey to fit within human timescales. The laws of physics as we understand them place strict limitations on our ability to physically traverse intergalactic space. This is the harsh reality promised in our title, a recognition of the profound mismatch between human scales and cosmic scales. We are ephemeral beings contemplating journeys that would span millions of generations. There is humility in acknowledging these limitations. Yet this isn't the end of our story, but rather the beginning of a more nuanced understanding. While biological humans cannot physically reach other galaxies with any technology we can currently envision, this limitation opens other pathways worth exploring. First, we must recognize that we already reach other galaxies through observation. When you look at Andromeda on a clear night, photons that travel 2.5 million years are interacting directly with your retina. In a very real sense, a physical connection is established. Our increasingly powerful telescopes extend this observational reach. The light collected by the James Webb Space Telescope comes directly from galaxies billions of light years away. We touch these distant shores with our instruments, if not our bodies. Second, while physical human travel to other galaxies may be impossible, information transfer across these vast distances remains viable. Radio waves, laser signals, and other electromagnetic communications can bridge intergalactic space, though still constrained by light speed. A message sent today to Andromeda would arrive 2.5 million years later. While this time frame exceeds human civilizational spans, it represents a form of connection, a cosmic message in a bottle cast into the future, carrying human thought across the intergalactic void. Third, while biological humans may not make these journeys, our technological descendants might. Advanced artificial intelligence systems, perhaps carrying human knowledge and values, could potentially operate over the timescales required for intergalactic travel. Such systems designed for extreme longevity and self-repair might maintain continuity of purpose across millions of years. They would not be human in the biological sense, but they could represent an extension of human consciousness and creativity into the cosmos. Fourth, while current physics prohibits faster than light travel, our understanding of physics continues to evolve. The history of science teaches us humility. What seems impossible within one paradigm may become conceivable within another. Quantum mechanics revealed a reality stranger than classical physicists could have imagined. General relativity transformed our understanding of space, time, and gravity. Future breakthroughs may reveal aspects of reality that open new possibilities for cosmic connection. So what really happens if you try to reach another galaxy? The answer depends on what you means, what reach means, and how we define success in such an endeavor. The question itself evolves as our understanding deepens. If you means biological humans using foreseeable technology, then attempting to reach another galaxy results in a multi-generational journey spanning millions of years, effectively a one-way mission extending far beyond any individual or civilization's lifespan. But if you means humanity's extended presence, our knowledge, our questions, our creative essence, then reaching other galaxies becomes a project unfolding across cosmic timescales, carried forward by both our biological and technological descendants. In this broader sense, attempting to reach another galaxy becomes not a single journey, but a cascading series of advances, each extending our reach incrementally. We have already begun this process through our astronomical observations and space exploration. Each step, from Earth orbit to the Moon, from Mars to the outer solar system, from nearby stars to the edges of our galaxy, builds capacity for the next. The path to other galaxies, if it exists at all, lies through these incremental expansions of human presence. Perhaps the most profound revelation is that the harsh reality of intergalactic distances doesn't diminish human potential, it contextualizes it. We exist in a universe of certain properties, including vastness beyond immediate human scales. This is not a limitation, but a defining characteristic. Just as fish evolved to navigate water and birds to soar through air, humans evolved to navigate the scales of our immediate environment. Our capacity to conceptualize scales far beyond our direct experience, from quantum realms to cosmic expanses, represents an extraordinary evolutionary achievement. This cognitive reach, this ability to comprehend realms we cannot directly touch, may be humanity's most distinctive trait. We may never physically reach another galaxy, but we have already reached them with our minds, a feat no less remarkable for being non-physical. The harsh reality, then, contains within it a profound beauty. We are creatures who can understand our own limitations. We can grasp cosmic scales that dwarf our physical existence. We can contemplate journeys beyond our biological lifespans. This capacity for transcending our immediate constraints through imagination, mathematics, and observation connects us to the cosmos in ways that physical travel alone never could. We touch distant galaxies through the light we gather, the patterns we discern. If we reframe the question from can we physically travel to other galaxies to how can we meaningfully connect with the broader cosmos despite physical constraints, new possibilities emerge that honor both the harsh realities and the boundless potential. Perhaps in the distant future, some form of consciousness with terrestrial origins will indeed reach other galaxies, whether through technologies we cannot yet imagine, evolutionary changes over cosmic timescales, or forms of connection we have not yet conceptualized. But even if this never occurs, even if the gulfs between galaxies remain forever unbridgeable by physical entities, the very fact that we can contemplate these distances, calculate them precisely, and wonder about crossing them represents a kind of cosmic connection already established. In the end, the harsh reality of intergalactic travel reveals something profound about human consciousness itself. We are beings capable of contemplating journeys we may never complete. There is both limitation and liberation in this truth. As we conclude our cosmic journey, we find ourselves in a place of paradoxical understanding. The harsh reality of intergalactic distances places physical travel beyond our immediate reach. Yet through our observations and contemplations, we already touch these distant shores. We are simultaneously bounded and boundless, confined to our local cosmic neighborhood by physics as we understand it, yet connected to the farthest reaches of the observable universe through the light that reaches our instruments and the mathematics that describes what we see. Perhaps this paradox itself offers the most meaningful answer to our question: what happens if you try to reach another galaxy? You discover both the limitations of physical travel and the unlimited reach of human consciousness, a journey of simultaneous humility and wonder. As you drift towards sleep, carry this cosmic perspective with you. Your body rests on Earth, bound by gravity to this pale blue dot, while your mind soars across intergalactic voids. Comprehending distances that light itself takes millions of years to cross. There is comfort in this dual nature, in being both small within the cosmic expanse and vast in our capacity to comprehend it. Whatever dreams may come, know that you participate in the universe's greatest wonder, consciousness that can contemplate itself and its cosmic home. If you found peace in these cosmic contemplations, join us for future journeys through space and time. Subscribe to our channel for more explorations of the profound questions that connect our brief human existence to the eternal dance of stars and galaxies.